Hello everyone, welcome to our presentation on the vulnerabilities in the RSA crypto system. RSA is foundational in secure data transmission, but no system is bulletproof. Today, we're exploring 6 algorithms that could potentially crack RSA. We'll briefly explain how these algorithms work and discuss the conditions that make RSA parameters secure. Over the next few weeks, we'll be implementing and testing these algorithms against various RSA setups. Our aim is to deepen our understanding of RSA's limitation and to advance cryptographic security. Let's dive into our first category, factorization attacks, which aim to break RSA by decomposing its key component, the composite number n. Specifically, we're looking at the general number field sieve, or GNFS. This is an advanced algorithm that improves upon its predecessors like quadratic and rational sieves. It's designed for efficiently factoring large composite numbers. In GNFS, we choose rational and algebraic bases and sieve for numbers that are products of primes from these bases. This leads to a matrix representation, and by applying linear algebra, we identify perfect squares that help us attempt to factor n through the difference of squares method. GNFS stands out because its sub-exponential complexity makes it the most efficient choice for factoring large general numbers. Our second category focuses on low private exponent attacks, where the RSA system can be compromised if the private exponent d is too small relative to the modulus n. A classic example of this is Wiener's attack. This method utilizes the equation E times D equivalent to 1 modulus phi of n, and the fact that E divided by n is approximately k divided by d, to pinpoint the correct fraction k divided by d in the continued fractions expansion of E divided by n. In practice, we apply the Euclidean algorithm to E and n, yielding a sequence of quotients that will be our call for k and d. We look for pairs that satisfy specific conditions, like d being odd and phi of n being an integer. Once we find such pair, we solve a quadratic equation to identify the primes p and q, the building blocks of n. This attack is most effective when the private exponent d is small, specifically less than 1/3 of the fourth root of n, and when the primes p and q meet certain conditions. So, if d is low and p and q are closely related, your RSA system is potentially at risk.
Thanks, Nacho. I'll start with the Franklin-Reuter related message attack. This attack became known in the late 90s and targets the RSA encryption algorithm's multiplicative properties. The attacker typically uses 2 related messages, M1 and M2, equipped with the same public key. By applying the Euclidean algorithm for polynomial GCD to these 2 messages, the attacker can find the greatest common divisor that can reveal the private key. The crucial condition for success in this attack is a known mathematical relationship between the 2 encrypted messages, M1 and M2. Let's dive deeper into how Franklin-Reuter works. Step 1 is to acquire 2 related messages that are equipped with the same public key. Step 2 involves using the Euclidean algorithm for polynomial GCD to extract the polynomial that defines the relationship between these 2 messages. Step 3 is the extraction of the private key, enabling the decryption of any message equipped with the related public key. Moving on, let's look at the partial key exposure attack. Originating in the 2000s, the attack leverages corpus methods and lattice-based algorithms. In this attack, even a fraction of the private key d, known as the fraction of d, is sufficient for an attacker to recover the entire key. The conditions for success hinge on how much of the fraction d is known. The more you know, the easier it is to mount a successful attack. To further clarify, let's break down the partial key exposure attack into its components. The first step involves obtaining a known portion of the private key, referred to as fraction D. The second step calls for the use of lattice-based algorithms to compute the potential private key candidates. Finally, the third step allows the attacker to confer and recover the full private key D, thus compromising the RSA encryption.
Short pad attack can be used when padding is misconfigured. Let's say Alice wants to send Bob a message M1. She pads the message M with some random number R1, which is k bits long, then encrypted it with Bob's public key. So we can write C1 as 2 to the power of k times M plus R1. However, this message is somehow intercepted by Eve. And since Bob didn't receive the message, he asks Alice to send the message again. This time, the message M is padded M2, producing an encrypted message C2 equals to 2 to the k times M plus R2. Now Eve captured this message again, and she can recover the plaintext efficiently. Let's say f1x is equivalent to x to the e minus c1 mod n, and f2x is equivalent to x plus delta to the power of e minus c2 mod n. Well, delta is simply r2 minus r1, and x to the e is just c1. By applying the techniques mentioned in Franklin-Rader attack, Eve can find a degree 1 monic polynomial to recover M2, which can be transformed to M easily. Hastad broadcast attack is proposed by Johann Hastad in 1988, and the name suggests it works when involving sending the same message to multiple recipients. Suppose a message M is sent to k people. For each recipient I, the message is encrypted with a public key such that Ci equals to M to the power of Ei mod Ni. For simplicity, we assume all recipients use the same encryption key, E equals to 3. Hastad claims that if the number of recipients k is greater than or equal to E, then the attacker can recover the plaintext with only the ciphertext and public keys. So the theory of these attacks is based on the Chinese remainder theorem. According to the theorem, we have C equals to M cubed mod N1 times N2 times N3. And since the plaintext M is less than Ni for any I in the recipients, by multiplying these inequalities together, we'll have n to the power of k less than the product of On. That means we can get rid of the modulo and the equation will just become C equals to M cubed. So the attacker can simply recover the message by finding the third root of C. The last thing I'm going to talk about is how we are going to set up our experiments. Our goal is to analyze how large the parameters should be, so they are considered as secure, namely P, Q, E, and D. For each parameter, we are trying to find the maximum value that the text can finish within the time allowance. Then we will repeat the process several times to reduce the errors due to randomness. Lastly, we will estimate the proper choices of these parameters based on the results we have. As the time and hardware resources are limited comparing against real hackers, the challenges are mostly from the implementation of these algorithms.